This is video 2 for chapter 20, and at the end of this video you should be able to balance a redox reaction by the method of half reactions. In this video we are going to cover how to balance reactions in acidic solution. So you might be wondering why we're going to talk about balancing reactions, because that's something you actually learned how to do back in 9th grade physical science. You review it again in 11th grade chem. But balancing redox reactions is a little bit more tricky because it does involve the transfer of electrons. Whenever you balance a reaction, the first thing you have to remember is to balance it according to elements so that you obey the law of conservation of mass. So you go by element, through element by element to make sure each side has the same number of atoms. But you cannot forget that it's also important that you balance total charge, so that overall electrons are not lost in a chemical reaction, or overall they are not gained. So not only does the number of atoms of each element have to be balanced, but so does the charge overall. So if we look at an example, like you have one written on your sheet, right now if you look, we have one tin atom on each side of the equation, and we have one iron atom on each side of the equation. So according to the conservation of mass, this reaction is balanced. But if you were to be careful and check your charges, on the left-hand side of this equation, we have a total charge of +5. And on the right-hand side, we have a total charge of +6. Since they're not the same, this reaction is actually not balanced. So we have to learn how to balance it. So what we are going to do is something called the method of half reactions. And to balance something according to the method of half reactions, you want to split the oxidation process from the reduction process. Now it doesn't really matter which one you do first. So let's just start with tin. We're going to start on the left-hand side. I see tin in a +2 state with aqueous. And then on the right-hand side, I see it in a +4. And you're going to have to bear with the smartboard during this video because it has been kind of screwing things up lately. So I'll try to make it look as neat as I can, but the board isn't exactly cooperating. So the only thing that's messing this half reaction up, and first of all, kind of ask yourself, which half reaction have I just written? Have I written the oxidation or have I written the reduction? And go back to the previous video's notes if you can't remember. But since our oxidation state's going from a +2 up to a +4, this is the oxidation reaction. So this one is for oxidation. And the only way to get this to balance is to lower its charge on the right-hand side. And the acceptable way to lower charges is by adding electrons. So since this is a +2 on the left side and this side is a +4, I'm going to add 2 electrons. Remember, electrons have negative charges. So if I add 2 electrons to my 4 positives, I now have an overall charge of +2. And I have balanced this half reaction, both mass and charge. So I'm going to do the same thing with the reduction half reaction. So I'm going to look at what is being reduced, which is the only other species in the equation. So I have iron with a +3 charge. And then, in addition, over here I have iron with a +2 charge. So we're kind of in the same situation we were with the tin. The iron atoms have been balanced, but the charges aren't. This time, it's the side on the left that's actually more positive. So on this side, I'm going to have to add only 1 electron to lower that down to a +2 charge. Okay? So I've balanced each individual half reaction, but I still need to recombine them to get an overall reaction like I have up in black on the above. So the problem is that in a final balanced reaction, I cannot have any electrons gained or lost. So if you look at your green reaction, you're gaining 1 electron. But in the blue reaction, you are losing 2 electrons. The number of electrons gained has to be the same as the number lost. So to make that work, I'm going to multiply this entire reaction by 2. And if I do so, I think most of you could see that it would become 2 electrons plus 2 Fe plus 3. And that will make 2 Fe plus 2. And now what I'm going to do is I'm going to add my blue reaction to my final green reaction. And I'll do that for you down here. So if I think of aligning my arrows and looking to see what cancels on the left side, the 2 electrons on the left side in green will cancel with the 2 electrons on the right side in blue. And so what I'm left with is tin 2 aqueous plus 2 Fe plus 3 aqueous makes tin 4 aqueous and 2 Fe plus 2 aqueous. And what you want to do when you're done with a reaction like this is you just want to double check, is it really balanced according to both mass and charge? So if we look at the number of atoms of tin, there's 1 on each side. The number of atoms of iron, there are 2 on each side. Mass is fine. Let's look at our overall charge. Now on the left-hand side, I have positive 2 from the tin plus 2 times positive 3, or positive 6 from the iron. So that makes a total of a positive 8. On the right-hand side, I have a positive 4 from the tin and 2 times positive 2 from the iron, or again, a positive 8. So the reaction that you see in black, right here, is our balanced chemical reaction. Now, I know that this video is a little bit longer than most that you watch, but there are steps to balancing these. That reaction we could balance without determining whether it was acidic or basic. But most reactions will either be in acidic solution or basic solution. So I'm going to give you a moment to fill in your directions for balancing reactions in acidic solution. You, in fact, just pause the video now so that you can take the notes that you need. And then when you're ready, we'll do this process for this example. Okay, so hopefully you're ready to now start this reaction. So following step 1, we're going to divide the reaction into 2 incomplete half reactions. So you kind of want to take the things that look alike. So I'm going to split the MnO4 minus aqueous, and I'm going to put that on the other side with Mn plus 2. Okay, and that's also aqueous. Now, step 2 says to balance each half reaction. So before I even write the next half reaction out, I'm going to balance this one in blue that I've written. So it says to balance elements other than hydrogen and oxygen. So in this blue reaction, the only thing that's not oxygen is the manganese, and it's balanced right now. So I don't have to do anything with that. Then the next part is to balance the oxygen atoms by adding water. So on my left side of the equation, I have 4 O's. So that means on the right-hand side, I have to go add 4 water molecules so that the O's are balanced. Then it says to balance the hydrogen atoms by adding H+. So in adding water to the right side, I've now added 8 hydrogen atoms. So on this side, I'm going to add 8 H pluses to get the hydrogens to balance. And then the last step for balancing says to balance the charge by adding electrons to the side with the greater positive charge. So let's look at my left-hand side. I have 8 positives and 1 negative. That's a total of positive 7 on this side. On my right-hand side, I have a total of positive 2 from the manganese. The water is neutral. So the side that has the greater positive charge is my left-hand side. And to get the charges to be equal, I'm going to have to add 5 negatives, which I'll do in the form of 5 electrons. So I've balanced my first half reaction. Now we're going to move on to our second half reaction. I'm going to take the C2O4 minus 2 aqueous, and I'm going to put that in the same equation as the CO2. Now, if you read the steps again, eventually these steps need to be something you memorize, but I think if you do enough problems, you won't have any issue with that. So go again, we've balanced each half reaction first by balancing the elements other than hydrogen and oxygen. So because I have two C's on my left side, I'm going to put a coefficient of 2 out in front of the CO2. So my C's are now balanced. Then it says to balance oxygen by adding water. Well, in this case, there are 4 oxygens on the left and 4 oxygens on the right, so I don't have to add any water. And because I didn't have to add any water, I don't have to add any H+. The only thing that I have left now is to make sure that I balance my charge. So if you look at this green reaction, on this side you have a charge of -2 overall, and on the right-hand side you have a charge of 0. 0 is the greater positive charge, so I have to add 2 electrons to this side. Okay, so what we have now done is balanced individually each half reaction. So we're ready to move on to step 3. Now it says to multiply each half reaction by some integer so that the number of electrons lost in one of the half reactions is the same as the number gained in the other. So if we look at our blue equation, we have 5 electrons being gained, but in the green equation, we have 2 electrons being lost. The easiest thing, since they're not the same number, is to multiply the blue reaction by 2 and to multiply the green reaction by 5. Now you're going to want to make sure you do that part carefully so that you can transfer all of your numbers through. But when you are done, you should be able to then add the 2 reactions together and simplify and to recheck your answer. So I'm going to go through all of the steps. If you want to do this on your own and just check your final answer, feel free to do that too. But I don't want to skip steps for those of you that might feel you need it. So what I'm going to do is I'm going to transfer these, and I'm going to distribute my 2 numbers across and do each step. So in the blue reaction, I would end up with 10 electrons. And I'm going to leave states off just to make life a little easier. I would now end up with 2 MnO4 minus 1 and 16 H+. That's all on the left-hand side. On the right-hand side, I would get 2 Mn plus 2 and 8 H2Os. So I always think it's a good idea to just double check that you didn't forget something as you transferred that 2 through. And then do the same thing on your green reaction. And I line up the arrows usually. So now the green reaction I'm multiplying by 5. So I have 5 C2O4 minus 2. And then now I have 10 CO2s and 10 electrons. So now your very last step is to add these 2 reactions together and simplify as you go if you can. So 10 electrons will cancel out with these 10 electrons. And you know you're doing something right if the electrons disappear. You should never have electrons in your final answer. Okay. So if we look at what transfers down, I have 2 MnO4 minus, aqueous, plus 16 H+, and that's also aqueous, plus 5 C2O4 minus 2, and that's aqueous. On the right-hand side, I end up with 2 Mn plus 2, aqueous, 10 CO2s, and those were gases, and lastly 8 waters, which we all know, I hope, are liquids. So now what I would suggest you do on your own is to go through and make sure, does each individual element balance? And I think you'll find that they do. But you also want to make sure that the charge is balanced. And that part is something a little new to you, so I'm going to show you. On this side, we have a -2 from the 2 MnO4 minus 1. Here, and then we have 16 and a minus 10. So when we simplify all of this, you get a positive 4. And if you look at the other side, the only charge is a positive 4. So we've balanced this correctly. So hopefully now you feel a little comfortable balancing reactions in a solution. And I think I've given you one to try on your own in your packet.